Good morning. Welcome to episode number 8 of the ZOOMTOWN experiment. For today's episode, we're going to be taking a look at the TCRT5000 photoreflective sensor. As already mentioned in previous videos, we're going to be utilizing line following to direct or guide the robots, the Zoomies, around the layout wherever there is straight road travels. Also mentioned in a previous episode, it's going to be very difficult to utilize line following for turns. But nonetheless, for straight line travel, we're going to use line following. Now, this particular system that I got to set up for it, I want it to be fairly robust. And it's all going to start with that sensor. Now, I've already got some good experience with this sensor. I've used it on a number of other projects in years past, and I really like it. But for this particular project, I wanted to dive a little deeper into its capabilities. Before we get into the details, let's take a look at what we're going to cover in this video. We'll be looking at the purpose for this sensor, a brief explanation of the photoreflective sensors. There are analog or digital types. Analog will be used for this project. We could go with either a single or a dual sensor arrangement, and I'll explain why I selected one over the other. We'll take a technical detail briefing where we'll look at the datasheet, the schematic, and the code. Finally, we'll go through and look at the guideline that will be sensed for our test here today, and we'll do some practical testing using CNC. Yep, you saw that right, CNC. I'm going to use my CNC machine to move the sensor so that we can get precise feedback data on how it senses, the sensor senses and reads information about that line. And finally, we'll have an analysis or review of the sensor to see if it performs for our Zoomie. Here you can see the size of the sensor. It's very compact, and that fits in well with our Zoomie's overall parameters. Now, I've done a video a few months back on a photosensor for the tachometer project. That one had digital output. It was either on or off. This sensor is analog. So what it will output is a signal proportional to the amount of light reflecting back on it. And that works well for line following because we can use that analog signal or value to adjust our travel left or right more precisely, so to speak, as opposed to just simply saying, oh no, the signal's on, and go flying over in the opposite direction until the signal goes off. So this lends itself very well for line following. I decided on a dual sensor arrangement to straddle the guideline. This arrangement is easy to deal with in code, being that if both sensors have the same value, the Zoomie is centered over the line. Also, having two sensors, it is quick and easy to determine if you're on the left side of the line or on the right side of the line. And that makes it very easy to get back on the track where you need to be. It also provides more data to make better decisions to make those corrections or changes in direction. Let's move on, and I'll show you this all set up in my test rig that I set up for this video. I wanted to have some information regarding how these sensors see the line that we're following, how that data coming into the PICO, and how I can use that to adjust course or direction. Now, this little jig here only holds two of the sensors at about the width I'm planning for the Zoomie. It mounts via this little hole via a 1/4-20 screw out on my CNC machine. And what I'm going to do with this is move this across that line at a controlled velocity. That will allow me to capture those analog readings into the PICO, and then that data I can further analyze in a spreadsheet. Now this looks like a jumble of wires, and it somewhat is for what we need to get essentially 4 wires for each of the sensors. So I got 8 wires coming back to the breadboard. I won't go into a lot of detail here other than just to let you know that I've actually got this configured where I can wire it up a couple of different ways with different resistor values and such to do further testing out on the CNC machine. But before we get anywhere near that, let's go ahead and take a quick look at the schematic so that you can see how all these components get wired up. On the schematic, you can see that I'm dealing with analog inputs. I'm going to most likely be using ADC1 and ADC2. Doesn't really which of the 3 that I would use. But as wired in the schematic at this time, it's 1 and 2. We're going to also get our 3-volt output from the PICO, and that will go into the transistor's collector via a 4K7 resistor. And that is I'm experimenting with that value up and down, and right now it's seemingly pretty good. If you look for other schematics, you'll see often 10K is used for this resistor. In my application, I think 4K7 is working a little better. But that gets wired into the transistor's collector. The emitter just gets simply connected back to ground. The LED, which is an infrared LED, I'm supplying 5 volts to that through a 120 ohm resistor onto the anode, and the cathode goes back to ground. There's a tremendous amount of data in the datasheet for phototransistors. They are, as simple as they are, there's actually a lot of stuff going on here because you've got the 2 components, the LED and the transistor. What I was really looking for out of this was one, its operating distance, how far I need the sensor from my markings. 2.5 millimeters is what they recommend. For those here in the US who like inches, that would be 0.1 inches, or about 3/32, a little more than that. Some of the other things that I was looking at, I always have to watch for current, and that'll make more sense as this project progresses along. We have to keep track of how much energy or power our Zoomie is using so that our batteries don't get depleted too early. So I want to keep each component down to a minimal amount of current draw. So I just quickly scanned through here, found some of the current ratings, a milliamp for up here, another milliamp there for typical output current, and I think I found a few more here. Forward current for the infrared LED, 60 milliamps at with a forward voltage of 1.5 volts. We've got again milliamp and let's see, 100 microamps on that one. Nanoamp here, as they're saying, 10 nanoamps. But again, the currents are all, for the most part, fairly low, so I'm not going to get too worried about it at this time. And those were about the primary things. The package size, I mean, it is what it is. It's compact. I'm not going to complain about that. But that pretty well was my major areas of concern. And then, of course, reading it, if it would provide a time or a limitation on that, and I don't recall seeing that anywhere, so I can assume I can read it as fast as I want to and as frequently as I want to. Now, I won't bore you with a lot of details about these programs. They're just test programs, so they're rough and somewhat crude, but they do provide me with a way to either capture data for further analysis, or the other side of the coin is I want to determine how long it takes to actually read this sensor. If it takes 100 milliseconds to get an analog reading, that's not going to work very well for our overall process. So one of the first programs I've written for testing is this one I'm calling line send ticks. That'll make sense here in a second. We're going to import our library of time and get a pin, set up a couple of analog channels on 1 and 2, and then I'm going to have a loop here that'll just repeat 10 times. And we're going to, right here, This line says ST equals time ticks microseconds. We read the two values from the sensor, and then end time, ET, reads time is equal to time ticks microseconds. So the duration it took to make these two reads, one for the A channel, one for the B channel, is recorded in this value, or in these two values. That is calculated or broken out by taking the difference between ST and ET using the time function to do that for us. Then we print it or add it to a total time counter. So I'm adding in that value for two reads to this variable. We're going to sleep for 100 milliseconds and then repeat this loop. And this is just to slow things down so it doesn't go zippity fast. Doesn't really affect my timing above. After it does this 10 times, it'll exit out of the loop. Then we're going to calculate the distance or the time per read, taking the total amount divided by the number of lines, meaning how many times we went through this loop, times 2, because we make 2 readings per once through the loop. And then on this line here, it will print out the number of microseconds it takes to make an analog read. So we'll go ahead and run this program so you understand what it's doing. And it's telling me I've got 24.4 microseconds of time to read or make an analog reading from this particular sensor. Overall, that's not bad. I would, of course, wish it were faster, but 24.4 microseconds should work perfectly well within what I have envisioned for the overall Zoomie program. So that data is pretty good. Then this particular program is the one I'm running when I'm out at the CNC machine. Most of it's the same, but what I add in here, we open up a data file to write this data in. Gets written to mydata.csv so that I can take that and import it into a spreadsheet after I copy it off the PICO and back into the computer. And we get through, we take our readings, then I create the line of text that gets written into the spreadsheet with three values, one that'll go in each cell, 1, 2, 3, or column, however you look at it. And then this will be counted up 10 times or 100 times in this case to get all the readings while that jig is moving across the line. We go through, get that, and then the data is written to the file. Let's take a look at a video showing you this whole setup out on the CNC machine. Out at the CNC machine, this is what we're actually using to read the data with our sensor and the PICO. Now I'm going to program the CNC machine to position over the top. I'm holding it up at an angle so you get an idea of the visualization. It'll start here in the middle of the line. It'll move completely this way off of our guideline, so this sensor is beyond it. It'll wrap it back to the center, and then it'll go off to this side back to center. And I'll do that for 3 different types of guidelines. Here it's pure white to our dark gray, a medium gray to dark gray, and then the triple color method, which is what I really have already on the layout painted. And that's white, medium gray, and dark gray. And I think that's going to give me a greater range of analog readings from one position to the next. So it looks a little bit less like a digital transition being on or off. But when we run it, that's all that'll happen. This will zip back and forth like so. The PICO will record it, and then we'll get over to the spreadsheet and take a look at the data to see the effects of that. While this may look a bit complicated, it's really not too bad. Then I program the CNC machine to move the equal distances off from center line off to the left, center line off to the right. While it's moving, this program is looping through, recording the data into that data file. And because I've got 3 different representations, that will allow me to analyze the transition from, we'll say, one color to the other color with this photo sensor. As it moves over, it'll transition in the tricolored version of the line. It'll transition from dark gray or white, medium gray, and then dark gray. And then we'll go over and repeat that same reading on the left side. Looking at the data I collected in a spreadsheet and graphed out so that instead of looking at raw numbers, we've got a graphic representation of what that photo sensor sees. Now, if you want to look at it from a very simplistic point of view, the blue line, or the blue here, is showing an off state down below. An on state is way up above. So you could think of it almost looking like on an oscilloscope, where it's just simply going to read on or off in a digital form. But what is important to me is this slope here. This is the transition from one color to another color, or I should say from the center of our guideline to the far edge of the guideline, way out on the roadway surface. Now, the more sloping this is, that's a more gradual transition, which gives us a better range of data from which to make decisions on how I should maneuver the car back. It's very unlikely this will be directly proportional to, say, how many inches or millimeters I need to adjust my position. But it is an analog value that is over time over distance. Now we can see here it's not too bad. Don't worry about the blue here, that's transitioning off the other color. But this first one here and this one here is when we're going from the white line transitioning outward. Now we go to, this was the white guideline version. The gray guideline version is a little bit more dirty. You'll see that I didn't get as good a readings on it, and that could be due to electrical noise out by a CNC machine. But you do see somewhat of a slope, a little more slope here than on this one. Same thing over here. And then finally, this is the white and gray guideline, and we've got an even greater slope there, 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 and there. So I'm really liking my decision to go with 3 colors. As much of a pain in the butt it was to paint all that, I think it's going to give me overall more data and better data from which to make decisions for course corrections. Overall, this sensor performed really well for me. There's a couple of little hiccups here and there, but I think mostly what I discovered in that was that it had to do with the wiring on the breadboard, etc. So I'm going to ignore that data. But everything else about it is working pretty darn good for what I want in a sensor for line following. Now, I'm not the only one that's chosen this sensor for this purpose. Many others have as well. But in analysis, here's what I think. It's got a decent range of readings, reasonably stable readings, and why I'm using the word reasonably is because I had a little bit of staticky looking readings on the gray and dark gray line. The time to take readings is reasonable at 26 microseconds. I'm not going to get overly concerned about that at this time. Price is reasonable at 22 cents each. Now, I'm really happy with that price for any type of sensor. It's easy to mount. I just need a rectangular hole, put it in, and a dab of hot glue will hold it in place. So with all that analysis and testing with a TCRT5000 sensor, I'm pretty confident I've got a sensor to go forward with in the design of the Zoomie. Next week, we're going to be taking a look at a color/gesture sensor. I'm not really concerned at all about the gesture. That won't help me for what I want. What I want to be able to do is sense a color accurately and consistently and treat that color reading as if we were reading a road sign. I don't want to get into character recognition or anything like that, but if I've got a color that I can detect, I can maybe differentiate between a stop or a yield condition, something to that effect. So we'll be taking a look at that sensor next week, and I hope to see you then. Thanks for watching.